Talk about oscillations. So we're looking at motion that repeats. And we have two basic systems that we're going to consider. There's a mass on a spring, and there's a pendulum. And I'm going to talk about them in some detail as to how they do what they do. Bowling ball pendulum right here. It's at its equilibrium position, okay? If I pull it a little bit to the side, I can feel, oh, heavens, there's a force that makes the bowling ball want to go back towards its equilibrium position. And if I pull it farther to the side, what do you think about the force? Bigger. And if I pull it farther, bigger. Oh, yeah, so the force gets bigger and bigger as I pull it to the side. Here's the thing, though. If I let it go, the force will pull it back towards its equilibrium position. When it gets here, there's no net force on it. There's very, very small forces near the equilibrium position. So when it gets back to its equilibrium position, will it stop? Oh, no. It's going to keep on going out the other side, and it's going to come back, and then come back to me like so. That's an example of simple harmonic motion. And we call it simple harmonic motion because it's simple, and it's harmonic. And that's pretty straightforward. Harmonic, what we mean by that is it's described by a sine function. We'll talk about that. We'll talk about that later. But you see this in any kind of a system where you've got an equilibrium position. And if you perturb something from its equilibrium position, you get a force that increases with distance. The farther I pull it from the equilibrium position, the bigger the force is. Then I let it go, and it executes this simple harmonic motion. Any case like this will result in a similar kind of motion. That's one classic kind of motion that we'll look at. Here's a second. A second kind of motion we'll look at is this. This is the mass on a spring problem. So I have a surgically altered slinky here. And a slinky is just a spring. And if I take this hamster and I hang it from the spring, what happens is the spring stretches because it's got this restoring force associated with it. And the hamster has this new equilibrium position, which is right here. Now, if I pull this hamster down from its equilibrium position, the spring is pulling. What's the direction of the net force? It's up. The spring is pulling up. And the only reason the hamster is staying put is because I'm hanging on to it. If I let go, the restoring force pulls it back towards equilibrium. When it gets there, does it stop? Oh, no. It keeps on going above its equilibrium position, comes back down, and then bounces up and down. So you get this mass on a spring motion. And that's our second type of simple harmonic motion that we'll consider. And it's because I've got a restoring force and I have a certain mass. And the motion looks like this. Now we're going to look at practical examples of this. Okay? We're going to look at practical examples of simple harmonic motion. And they are many. And we're going to start by doing an exercise as a class. I want you to stand up. Go ahead and squeak those desks. Go ahead and stand up. All right. So suppose you're walking down the hallway, and your legs are moving back and forth. Okay, ultimately, the motion of your legs, it's fixed at the hip, and the muscles that make your legs move back and forth are actually pretty weak. Mostly, what makes your leg, when your leg goes backwards as you're walking, mostly what makes it swing forward is just gravity. Go ahead and do this. Stand on one foot, and let the other leg just swing back and forth. Swing back and forth, forward, as if you're walking. It's got a certain natural frequency that it likes to go at, doesn't it? That's one of the things we'll find with simple harmonic motion. Try to make your leg go twice as fast as that. Doesn't work. It doesn't work. And you can see then you're using the muscles, and normally you don't use the muscles. Normally, you just let your legs swing back to its place. It's gravity that does it. It works as pendulum motion. And one of the things we'll talk about with pendulum motion is it's got a certain natural frequency associated with it. You can do the same thing with your arms. Go ahead and take your arms. If you're walking, your arms going back and forth like this. Pendulum motion. It's gravity that brings it back and forth. Try to make them go twice as fast. That's hard, isn't it? Oh, except suppose you're walking, and then you have to break into a run. What do you do with your arms? You shorten them up. Oh, yeah. So you got slow, and you have faster. You can do that, right? What's changed? The length. If I take a pendulum and I change its length, I can change its natural frequency, and so you can go a lot faster. So the motion of your arms and legs when you're walking is ultimately pendulum motion, and we'll talk about that. Go ahead and have a seat again. If you're walking down the road, or if you're running, we talked about the fact that your Achilles tendon has a stretch to it, right? You hit the ground, your Achilles tendon stretches, it launches you back in the air again. You're a mass, your tendon is a spring, okay? Same thing with the pogo stick. I have a spring, I'm a mass, it's a mass on a spring system. And you can have things that you model as simple harmonic motion, even if it's not like this. It's kind of like just bouncing up and down. And in all cases, at all times, the mass is in contact with the spring. This isn't. I go down, launches me back in the air. I'm in the air for a while, come back down. This motion always takes the same amount of time. It takes the same amount of time for it to go up, come back down, reach its starting point again. Okay, that's one of the things that we'll talk about. This motion is not true. I can go kind of like so, or I can go higher, takes longer, but the extra time is the time in the air. The amount of time in contact with the ground is always the same, because in contact with the ground, it's mass on a spring, mass on a spring, mass on a spring, oh yeah, mass on a spring. And when you're in contact with the ground, it's always the same, because it's mass on a spring motion. Okay, that's another practical case.